In the last few videos, I discussed how to solve systems of homogeneous equations with constant coefficients if my characteristic polynomial had two distinct roots as well as repeated roots. I now want to consider what happens with complex numbers resulting in these roots. However, before I do that, I'm going to look at what's called Euler's formula. The idea, I'm going to look at e to the alpha plus I beta t, so e to a complex number times t. And this is actually equal to e to the alpha t times cosine beta t plus I sine beta t. Alpha and beta are going to be real valued constants. And another important thing we'll need to know for this, alpha plus I beta and alpha minus I beta are known as complex conjugates. So if all I do is change the sign in the middle, these will be complex conjugates. So I want to look more into this formula. And I can start with some very, very basic manipulations. For instance, we can easily distribute this exponent. This would be e to the alpha t plus I beta t. We can use properties of exponents to say e to the alpha t times e to the I beta t. And so what I'm actually claiming here is that e to the I beta t is equal to cosine beta t plus I sine beta t. And I don't want to just take this for granted. I actually want to see why this might be true. Let's take a closer look at this e to the I beta t. If I consider the Taylor series, this would be the summation from n equal to 0 to infinity of I beta t to the n over n factorial. I can go ahead and write out a few of these terms. Anything to the 0 power is 1 and 0 factorial is 1, so the first term would be 1. I then have I beta t over 1 factorial plus I beta t squared over 2 factorial, I beta t to the third over 3 factorial, I beta t to the fourth over 4 factorial, I beta t to the fifth over 5 factorial, and I can keep going like this. The first thing I want to do is try to simplify these i's a little bit. I is the square root of negative 1. So I squared is negative 1. So this second term, or the third term here, is the same as negative beta times t squared over 2 factorial. I cubed would be I squared times I, so negative 1 times I. So I'm going to write this as negative I times beta t cubed over 3 factorial. I to the fourth is 1, so I have plus beta t to the fourth over 4 factorial. I to the fifth is just the same thing as I. So this is I beta t to the fifth over 5 factorial, and you can keep going. These are going to alternate between I, negative 1, negative I, and 1. The next thing I want to do is regroup. I want to consider all the things that don't have an I. So 1 minus beta t squared over 2 factorial plus beta t to the fourth over 4 factorial. And we can keep going. We'll have minus 6th power plus 8th power, etc. I'm then going to consider all the things that have an I. And I'm going to go ahead and factor out the I. So I have beta t over 1 factorial minus beta t cubed over 3 factorial plus beta t to the fifth over 5 factorial minus, and you can keep going like this. And if we look at this thing right here, this first term, this is exactly the power series for cosine beta t. And this second piece right here that I'm multiplying by I, That's exactly the power series for sine. So I have cosine beta t plus I sine beta t, which is exactly what I wanted it to be.